Good afternoon, everyone. My name is Wenyuan. I'm from Alibaba Damo Academy, and my team is building. It's the team behind the GraphScope. It's basically graph computing stack to deal with many kinds of different graph tasks. And today I'm going to introduce GraphScope Labs. Labs like kind of to address the actual diversity and complexity we have met in the real production graph computing like we are facing in Alibaba and from our community users. I will do this slide really quick. So basically, as mentioned by some previous speakers, actually the graph computing landscape is very diverse, and often one user may require multiple different graph tasks to be solved in a single pipeline, and that's the case in Alibaba as well. And so in this case, back in 2021, we built a graph computing system called GraphScope. I think it's very similar. The idea is very similar. So it's not to the previous. I don't know how to pronounce it, but okay. So basically, we want to give you a unified experience on a Python Jupyter notebook, and we support Grammy instead of Cypher because Grammy looks like more Pythonic in a way because lots of dot and bracing, and we also allow users to use Python to program some analytical algorithms and UDF, etc. And behind it is a distributed data flow runtime that enables some optimizations for graph operations, and we have a memory data store to store the data. And in this case, the graph is static, so it does not allow updates anyway. So we only basic some projections or create a new graph, but no updates or deletions to an existing graph. And so in this way, we actually can solve a pipeline like this. So because in a pipeline, data does not, a batch analytical pipeline does not really change during the process. So a user can program a Python notebook code, and we can parallelize it and run it on a big Kubernetes cluster. But however, real-life graph applications are more complex and diverse than we have originally thought, because there are multiplicity of workloads. For example, there are graph analytics, interactive queries, pattern matching, and graph neural networks. And the user may have different tasks or deployments require different data storage. For example, it may as we have seen all the systems from today, some user does not need durability, but we do need updates. And some users say, okay, I need to have ACID support, or the data does not change. We only need to reload every day, maybe at 0, at 12 a.m. each day, and to do one batch computation for all the data we have yesterday. Okay, so there are lots of different design choices for storage as well, and for the programming interfaces, they are very diverse as well. And we have GQL, OpenCypher, Grammy, and for analytical algorithms, they may want to we have all seen, people may not want original BFS, they want some customization, so they may want to have their own algorithm written. So they have prep or get scatter, GraphLabs, or PRE, and they want to do GNN, they can choose from PyG or DJL to program their model. And there are different diverse deployment modes and the performance needs as well. For example, it is an offline data analytical task, or it's online services. It's optimized for the latency execution time of expensive query, or it's just like we want to have really, really high query throughput and have really, really high number of queries processed each second. So, and this we dig even deeper, we find it is very, very diverse and complex indeed. For example, graph language, so many and different like performance requirements. We have graph analytics, we have different algorithms and different programming models, and we have GNN. So, for example, machine learning with graph embedding, random walk, GNNs. We want to do the sampling-based GNNs, or subgraph-based GNNs, or whole graph GNNs, and we want to optimize for inference, training, and for the storage, it could be read-only on static graph, and we want to support updates, and whether it is transactional, have some transaction guarantee, or it doesn't matter because we are in internet company. Sometimes we don't care for recommendation purpose and the streaming in memory on these, and whether it's a cold graph archive, maybe over Amazon AWS S3, or it's a property graph, RDF data, partition, vertex card, edge card, or hybrid card. Whether it's on GPU, and there are other applications as well, for example, key knowledge graph, hypergraph, etc. So how can we design useful tools to help users solve this problem? Our solution is make components composable. So, so in this way, we want to separate our system into multiple layers, like horizontally, and we have some vertical separations as well. For example, like this stack, and for like interactive query processing stack, people can maybe compose a graph database-like system or streaming processing system for like cyberprogramming. And maybe in the middle is like an analytical system, and maybe user just want to do a HPC style batch processing or MPI, or etc. And for GNN systems, the key maybe is to have good integration with either PyG or DJL, so user can leverage like existing graph GNN models. Yes. So I will skip to the details of everything, but I will focus on two areas. First is how we use the interactive query processing stack, and the other is how we design the storage stacks such that we can decouple everything. There are a couple of challenges for building the interactive query processing stack. For example, how can we support more query languages? Grammy is not a very beautiful designed query language, I can say, because it contains more than 100 different type steps, and each different type step may return different intermediate results, and it's very hard for us to write. If we want to implement each step as a step in a data flow engine, it takes forever. And not to mention we have Cypher, GQ, etc. Is it possible to build a single stack and we can support multiple languages, and how to effectively optimize graph queries? Yeah, I understand for some cases like handwritten queries are more effective, but in our case, for example, in Alibaba, we don't have the capability to support any users to optimize their Cypher query. That's true. They may choose to change the condition from time to time, and we can't babysit for our users. They are normally data scientists. So in that case, I think a query optimizer may still be useful in our case. And how to support more types of workloads. For example, we want to optimize higher QPS, or we want to do data parallel to lower the execution time of an expensive query. Here is our approach. So basically, we have multiple frontends that can take different query languages, and we try to identify a core set of we complement the relational operations with a set of very useful graph operations. In this way, but it's not complete. We cannot do the unbounded recursions, like recursive SQL in our case, but we only support sorted paths in our case. So I wouldn't say we fully support graphing over the cipher and GQL, but we can do it not too bad. And actually, we have some backdoor channel to just bypass that to our execution engine without query optimizing. And we have built a query optimizer based on Apache Cosine because we have adopted a large number of relational operations for our IR, and we have built a actually this is published in this year's ATC, and we built a graph-based catalog to capture for the cost-based optimizing. And the output of our optimizer is we can adapt it to different plan, and we will do a code chain. Actually, in this case, we didn't really care the real timeness like we have a logic or something, but here we all compile to C++ or Rust. And we run an actor-based execution. For example, here it's called high actor, and the high actor, I can't see. Okay, the high actor is actually built on C#. We have very similar design choices with the RageDB, and on this path is more like a scoped data flow engine, like for the data parallel distributed graph computation, and this yeah. Then I will move on to the problem of separating storage with the actual computation. It is very important for us because over the years we have built different graph storage to tackle our internal users' need. And if we really want to make the storage support all kinds of workload, it becomes very hard. We need to have an M times N integration here. So in this case, we want to have a common interface for engines to access graph data such that we can add more types of engine or more types of storage engine easily in the future. But understanding the complexity of graph storage abstraction is very crucial here. As we have already seen, it's very diverse, and the computing engines have different requirements as well. For example, if I have an analytical engine want to access a simple graph for PageRank, we won't use the property graph. We won't care whether the underlying graph is a property graph or RDF graph. We may care about whether it is partitioned, what is called edge cut or hybrid. But for other things, it does not care much whether it's static or not. So we designed a GRIN. It's our internal interface for accessing graph data. And the goal is to simplify the integration and from M times N to M plus N. And to achieve the goal, we only support read paths over an immutable graph. When the graph is changing, it can only access a snapshot of the graph, whether the snapshot is a hard copy or not. And currently, GRIN does not support writes. And the engine have to be integrated. I mean, the storage has to be integrated with corresponding computing engine to handle writes by themselves, but not with green. And actually, we follow a tree abstraction for all the graph elements, such as vertices, edges, partitions, and labels, properties, etc. And this is inspired by POSIX. And for example, a file descriptor can and cannot do something with, can or cannot do something with. For example, we cannot do a memory matching with a random a file descriptor. For example, a pipe, we cannot do that. API is written in C, which makes green portable to engines written in different languages. And we also define handles like file descriptors for different types of graph systems. Yeah, and green is currently still work in progress. And currently, we have adopted all the computing engines and 3 out of 5 storage engines with green. And the preliminary results show that the performance of overhead of green is always less than 10%, and with like LTO enabled, and or we have some fast FFI applied for cross Java and C++. And if you are interested, welcome to watch. It is a fully open source. Watch GraphScope/green for progress on GitHub. And further ahead, we plan to make green support more external storage and private to abstract graphs from other types of storage as well. And finally, I want to introduce Graph AR. It's actually also part of the storage layer. It is used for we aim to make this a common format and to make every different computing systems and different graph database can share data, can share graph native data. And besides, I think it can serve as a archive storage for graph data, maybe in a data lake, in object stores or file systems, such that some graph computing can directly down over such graphs without loading it in memory. And we want to use Graph AR to to support directly run algorithm and etc. Yeah. And the feature of Graph AR format supports the property graphs and the different representations for graph topology. For example, COO, CSR, and CSC. And we want it to compatible with existing widely used formats, include Apache Arc, Parquet, and less ideally CSV or TSV, because that's not column based. And we use Apache Spark for generate, load, and transform graph AR files. For example, user can only give us a CSV based graph AR, but we can still transform it to more efficient Parquet or Arc formats. And we want it to use in a variety of single machine and distributed graph processing systems, database, and other downstream tasks without too much constraints. For example, the degree of how many workers are there, or etc. And we want to enable user to conveniently perform operations without modifying the payload file. For example, we can only consume its adjacent list, or we can only pair some part of the properties, and we can easily insert any new properties or construct a new graph with the selected types of vertices, edges. We will want to make that easier. And that's a basic idea of how do we store the data. Actually, we chunked vertices and we separate its ID from its different properties into different chunks. So in this case, maybe some upstream tasks can can generate different properties in different batches. And for example, if we have column stores and we can store CSR, and we have offset table and maps all the vertices into multiple chunks of edges, and edges are chunked as well. So maybe vertex cut system can evenly consume edge chunks in this way. And we have YAML-based data other files to describe the schema of the property graph. We aim to make it compatible with the PG schema just mentioned. And the future of GraphAR is currently open source at Alibaba/GraphAR, and we aim to support more file formats, more standards, and user-defined data types, and more graph features such as RDF, time series, etc. And we want to implement some encoding optimizations for better out-of-the-core graph computation, and we will complete the Spark suite to create Spark files and the integration into with popular graph databases such as Neo4j Nebula, 2Graph, and some other graph release systems as well. And we want to explore the use of GraphAR for data lake for graphs. And we aim to make GraphAR vendor neutral. Maybe we will donate it to Apache Foundation when it matures. And the current contributors include we and Zhejiang Lab and Nebula Graph. They are all LDBC members as well. And the new contributors are very welcome. And the conclusion, GraphScope Labs is an ongoing effort to make our graph computing stack more composable to tackle diverse graph applications. And the areas covered by this talk is first the interactive query evaluation framework and a new story here. And you can scan more to learn more about GraphScope project. Thank you all.
Thank you. That's a lot of work, so congratulations on pushing this. Any questions to Wenyuan?
Interesting presentation. So all your execution engines, so there were two execution engines. One is more targeted towards kind of transactional sort of running queries, and the other one for analytics, is that correct?
Yeah, the one is for like see it's for maybe SMB interactive, and one for BI like queries. So because we do not want to do data parallel for SMB, obviously, because like any parallelization requires synchronization and lowers the query speeds.
Yeah. I see. Makes sense.
Does this intermediate representation is the same to both kind of querying and algorithms over the graph?
It's only for like some subset of scrambling OpenCipher and graph dimension QQ. It's only for this. It cannot like support like arbitrary graph computing algorithm. It's not Turing complete, I can see. So it's not currently support recursion, for example, with condition, with point, etc.
But is for the ones that you guys forward is it one intermediate representation for both like queries and algorithms, right?
Yeah, but not algorithms. Algorithms like we ran on different systems. We didn't cover it here. It's actually MPI. Yeah. So I think it's maybe for like this algorithm, it does not really help for even have a data flow system. So basically, I think the collective communication primitives is enough here.
Okay, any questions from here? Yes, one from Alistair.
On the graph archive, format. I was just looking at your repo, and it looks like you only support single labels. Is that right at the moment?
At the moment, yeah, but yeah, it's a working progress actually from Nebula to support multiple labels. But we are still figuring out how to encoding it with maybe Oracle Parquet is efficient to make it more efficient.
Sure.
Yeah.
And the other comment is I think it'd be worth having a look at the paper that was jointly presented to WG3 last week on some potential revisions to the syntax for content types and type names and labels and so forth before. I wouldn't. My recommendation would be get involved in what's going on in terms of what the Lex thinking before directly implementing PG schema, because I think PG schema is not going to be the end of that process.
Yeah, understood. So basically, currently, because we only support a single label, right? So we want to make sure that it conforms with PG schema, but it does not cover all aspects of PG schema. I don't think that's realistic at the moment. But your suggestion is great. We must follow and see like what the features to add, and we want to learn more from.
Yeah. I understand that. Let's talk, because
sure.
Otherwise you could sort of be behind the curve in terms of what's happening. It would be great if you were matching where things are going. So yeah.
Thank you.